So thanks everyone for joining in. We today have Debasmita, who is going to talk about noise and time optimized distributed scheduling for quantum circuits. Debasmita Bhoumik is a senior research fellow at Indian Statistical Institute. Prior to joining her PhD, she did her bachelor's and master's from the Calcutta University in computer science and engineering, and she was a gold medalist in her bachelor's. Um, so her research interests are in quantum circuit synthesis, quantum error correction, and machine learning. So on to you, Debasmita.
Yes, hello. Good morning, everyone. Let me share my screen. Is this visible?
Yes, yes.
Yeah, okay. So today I will talk about this recent paper, Distributed Scheduling of Quantum Circuits with Noise and Time Optimization. It is a joint work with Ritujit Majumdar, Amit Shah, and Professor Shushmita Sharma. One minute. Yeah. So first we will go through some introduction. Then there are three parts of this talk: circuit mapping, circuit cutting, and circuit scheduling. In the circuit scheduling portion, we have our contribution, and then we will show some experimental results, and we will propose one polynomial time solution of this problem. So first, as we all know that quantum computer nowadays is promising, but there are some gaps because we are currently in the NISQ era, that is the noisy intermediate scale quantum. Now, quantum in the quantum devices, the qubits are noisy and the number of qubits are also small. So we can see from this graph that if we run a Bernstein-Maserani algorithm circuit where the circuit size is half of the device size, then the fidelity drops. The fidelity higher is better because it is the closeness measurement. So suppose we are running this circuit in a 5 qubit machine, then the fidelity is good. But when the device size is increasing, the fidelity is falling. So how to evaluate the larger quantum circuits despite these challenges? So first we will see circuit mapping. So in NISQ devices, the connections between qubits are weakly coupling. So there is no all-to-all connection between the qubits of the devices. So the interactions are limited. Let us consider an example. Here we have considered a 5 qubit circuit. As you can see here, we are trying to map this into a 20 qubit quantum device. So how is the mapping? So qubit 0 is mapped to 1 here, qubit 1 here is mapped to device qubit 0, and so on. Now we have to do this C0, that is the C0 between qubit 0 and qubit 4. Then what happens? We have to do the C0 between this 1 and 7 here, but there is no direct connection. So we need to introduce some swap gates to bring this 7 near this 1, do the operation, and then again put it back. So we need 4 plus 4, 8 swaps total. So swap gates are needed, which increases the quantum error rate, because swap gates means C0 and their error names. So there are certain algorithms like Sabre-Ticket for efficient techniques of circuit mapping. This basically minimizes the number of swap gates. But minimizing swap gates while using low noise qubits for mapping is extremely challenging because these two requirements are orthogonal to each other. So as you can see here, the quality of the qubits varies in a quantum device. So in this IBM Guadalupe, not all qubits are of same error rate. The error rates are different. We can see from here by seeing the color code also. So not all qubits or all the interactions, that is the connection between qubits, have the same error probability, and we have to keep in mind while mapping the circuit to device. So there is a technique, Map-O-Matic, which considers the quality of the qubits during mapping. So it is basically a post-compilation routine that finds the best low noise subgraph on which we have to run a circuit if we have one system or more than one system. So suppose we have a circuit and an underlying device. So how should be the mapping? So Map-O-Matic first finds the best placement which minimizes the SAW without bothering about the qubit quality. So it first maps the transpiled circuit into the device. Once the mapping is done, it finds all other possible placements. So this structure, how many this structure can be found in this underlying graph. So it finds all the possible placements of the transpiled circuit on the hardware such that the number of swap gates doesn't change, because the swap gates is decided in the first step itself. So the Map-O-Matic basically search for matching subgraphs using the VF2 mapper in Qiskit. Now the score of the placements are calculated by the calibration data. This score is calculated from the single qubit gate, 2 qubit data, infidelities, T1, T2 errors, etc. Now once we get the scores, it basically finds top 5 or 10, how much you needed, top placements, and select the placement with minimal score, that is maximum fidelity, that is the best placement. So suppose, let's consider an example. This is a 6 qubit real amplitude circuit. Now what Map-O-Matic does, suppose we have the IBM Hanoi machine with us, then the Map-O-Matic basically maps this circuit into this device. So Q0, Q1 to Q5 are the qubits here. So Q0 is mapped to device circuit device qubit 2. So Q0 here is mapped to here, and so on. So here we can see the placements, and here the Map-O-Matic score. And from here we can see the topmost placement is with minimum score, that is the best fidelity, and we can check with various backends like Hanoi, Mumbai and other backends with various qubits what will be the best corresponding node and what will be the best Map-O-Matic score. That was mapping. Now comes the circuit cutting part. Why this is needed? Because in NISQ era the size of the hardware is limited. So suppose we have a larger circuit here. So here we are having a 9 qubit circuit, but this is a 7 qubit machine. This is a 10 qubit circuit, and this is a 7 qubit machine. We can't map this. Hence, we need circuit cutting, and moreover, reducing the number of qubits of the circuit by cutting can reduce noise itself. It is showed in the paper of Berlin in 2021. So how to do this cutting? Let us see one simplified view first. So circuit cutting basically decomposes an identity channel. So an identity operator I that can be written as sum of the outer products of the basis state. For example, 0, 0 plus 1, 1. Now suppose we have a state psi, we can write it as I psi. Now this I can be broken into the basis state, like here 0, 0 plus 1, 1, here we can consider the basis state as B. So outer product of BB, sum of it over psi. Now we consider this 3 qubit circuit. Here on first 2 qubits operator is U, on second and third qubit the operator 2 qubit gate is V, and we want to cut here. Okay, so we can write psi as operator as gate V23 applied, first U12 applied on 0, 0, 0, and then V23 is applied. Now we want to cut between U and V. So here basically we introduce the I and then write I in terms of this, that is the outer product of PB. Now we can just break this with U2, this gate we take the B, and this V23 we take the gate. Now what you can see that this 3 qubit circuit is now 2 qubit circuits. The number of qubits are reduced, and we can write the state as I. canonical product of these two states. Now this cut, so we have done a cut between U and V. So this cut incurs four different upstream subcircuit. Now what is this upstream subcircuit? For each cut we have to measure it in I, X, Y and Z basis and get the outcome. And for each cut we have to prepare it in 6 different downstream subcircuits. That is in 0, 1, plus minus and plus I minus I. Therefore, we need 8 to the power k summations for k cuts. And this is the deal because this is a time consuming classical reconstruction. Now there is a paper in 2021 called as Cut QC. It shows that we don't need these 4 upstream and 6 downstream subcircuits. We basically need 3 different upstream subcircuits and 4 different downstream subcircuits, because measuring a qubit in I or Z basis is basically corresponding to the same quantum circuit. So here from the figure you can also see that this is a 4 qubit machine circuit, and we want to cut it by this line. So the states are for the state gate observable different symbols are given, and there are 8 products O1 to O8 here, and Cut QC shows that with instead of IXYZ we need only IXY, and 0, 1 plus minus plus I minus Y we only need 0, 1 plus and plus I results. So instead of 4k terms we need instead of 8k terms we basically need 4k terms. And why 4k terms we can see from this slide. So we have a circuit, this is a 5 qubit circuit, and here is cutting. The 2 subcircuits are produced by cutting this key between the first 2 CZ gates. Now here we will produce IXY and measure it, and here we will prepare this 0, 1 plus and I. So these terms, so let us explain these terms. Here we have to measure I, X and Y. So this is for I, this is for X, this is for I, Y. So this is what is the probability of getting 0, 0, 0 when we consider I, what is the probability of getting 0, 0, 1 and so on. This is same for the subcircuit 2. This is for preparation, this is for measurement. So the classical post-processing involves summing over the products between the 2 subcircuits over the one cut made. So if the number of cut is k, then the complexity becomes big O of 4 to the power k. Now the part of circuit scheduling. So this is our contribution part, that is circuit scheduling. So let us have a list of hardwares. Here we have Manila, Quito, Nairobi, Guadeloupe and Hanoi for this diagram, and there are some circuits. So we have taken adder circuit, Bernstein, Vazirani, Grover, real amplitude, ripple carry adder and Trotter's circuit. So we have to map these circuits to these hardwares. Now let's consider this from this list of hardware. H mean belongs to H with the hardware with lowest noise profile. So that will be the best hardware in this list. So if then we don't give any constraint on the execution time, so if we have enough execution time in our hand, then the best thing will be to run all the circuits in the best hardware, which have the H mean noise profile. But this becomes a sequential execution, but it will give the best fidelity, which costs us the maximum execution time. Now fidelity is a measure of closeness between 2 quantum states. Now another thing can happen, the opposite scenario, that we don't consider the noise profile of the circuits, then we can parallelize it completely. So we can schedule all the circuits in different hardwares. This will require the least execution time, but what will happen, the fidelity will be worse because we have not considered the noise profile of the hardware. Now we have to come to a trade-off. So the optimum scenario is, given a list of circuits C and a list of hardware H, and we have some maximum allowed execution time tau j for each hardware, then we have to find an assignment Fij. such that the fidelity of the circuits are maximized because that is our goal, and the execution time will be within a certain limit, that is the tau. So for this, we design our scheduler known as time and noise optimized distributed scheduler. This scheduler uses integer linear programming to schedule the subcircuits to quantum hardware. To make this ILP, we need some variables, so we associate a variable xij. So it is 1 if subcircuit I is scheduled to hardware j and 0 otherwise. Now we have to define the constraints. So the first requirement is all the subcircuits should be assigned to some hardware, and this constraint should hold for all the subcircuits. So though it is one constant, it basically breaks down in number of C constraints, where C is the number of subcircuits. So summation should be 1. So the second constraint is, so for that let us remember what we have seen during circuit cutting, that each subcircuit may have multiple subcircuit instances depending on the number of preparation qubit and the number of measurement qubits. Because we have to do multiple preparation and multiple measurements for one cutting. Now all these instances can be scheduled together on same hardware, or we can also schedule them as individual circuit to different hardware, and we associate a value eta with each subcircuit such that eta will be 1 if all are scheduled individually, and eta will depend on this number of preparation qubit and measurement qubit if they are scheduled in a same hardware, not individually. Now we associate a maximum execution time Tj for each hardware G, because we don't have unlimited time to use these hardwares. Now this value tau can be provided by the user, and let Ti denote the execution time for each subcircuit. So we take a subcircuit, how much time it needed to execute on a particular hardware. Now this total execution time of all subcircuit to a particular hardware should not exceed the already fixed time tau. Now the constraint 2 essentially results in age constraints, the number of hardware, because we are doing this for one hardware and we have to do this for all the hardwares. Now how to calculate this Ti, that execution time. So suppose we have this real amplitude circuit, again the 6 qubit real amplitude circuit. We assign that T1 time is needed for the 1 qubit gates, T2 time is needed for the T qubit gates. So if we break this in timestamps, we can see that from the original circuit, we need the time is 2T1 plus 5T2. Now see, if we break the circuit in two subcircuits, then it automatically reduces. So the time for the first subcircuit is 2T1 plus 2T2. Time for second subcircuit is 2T1 plus 3T2. So it is, both of them are lesser than this 2T1 plus 5T2. So if you can parallelize this will obviously need a lesser time. So from here we can count the total execution time, that is summation over eta into time I. This tau can range from Tmax, when the Tmax we need more time if we schedule these two subcircuits in a same based hardware, it will be sequential, and when T mean, tau mean, when we parallelize them, and this tau mean is basically the maximum time needed between time 1 and time 2. Whichever is larger, we need that tau minimum at least. So now comes to our objective function. The objective function of this optimization problem is maximizing the fidelity. And now maximizing the fidelity means minimizing the overall score which we have gotten from mathematics. So this is the objective function defined. So Qij is the mathematical score and Xij is the flag variables we have seen in the ILP. We have to minimize this. Now comes to the experimental setup portion. We have carried these experiments using IBM Q simulation, Quasar and state vector. We have taken the noise models from these hardwares. We have written the noises in the table. And for the software dependencies, for circuit cutting, we have used circuit knitting toolbox package. We have used Mapomatic for finding the best layout and score for a circuit and hardware pair. And for solving the optimization problem, we have used the Simplex Academic Edition. So let us consider a case study. So for a 6-qubit triple ladder circuit, so this is a 6-qubit triple ladder circuit. This is the cutting. We have got 2 sub-circuits, and we can see the mathematics scores from here. So for uncut, there are 6 qubits. This was the layout for IBM Kolkata, and this was the mathematics score. And when we broken them into 2 sub-circuits, each has 4 number of qubits. This is out in Mumbai and this is the mathematics score. Now let's see what happens in case of fidelity. So along with triple carry adder, we have also considered 3 more circuits: real amplitude, trotterized, and Bernstein-Vazirani, all of qubit size 6. And what happens after cutting and during uncut, we can see here that in the uncut portion, the fidelity for no error mitigation is 0.759, and after cutting, the fidelity for no error mitigation becomes 0.792. So 0.759 to 0.792. This is the increase in fidelity. For measurement error mitigation, the result will obviously be better. So for measurement error mitigation, during uncut it was 0.787, and if we consider the measurement error mitigation, it is 0.843. The result is similar for the other circuits. So we observe an average % improvement in fidelity for distributed scheduling using circuit cutting over no cutting. And when no error mitigation is used, the improvement is 5.2% approximately. And when measurement error mitigation is used, the improvement is 4.89% approximately. And this measurement error mitigation, to implement it in Qiskit runtime, we have to select the resilience level 1. And as we have used the sampler to do this measurement error mitigation, MEM is equal to M3. We have also done this experiment for 10 qubit circuits, and here the trend is also similar. The improvement is better also. So when no error mitigation is used, the improvement for cutting was 12.38%, and when measurement error mitigation was used, the improvement was 21% over uncut circuits. Now we have done an experiment that if the number of sub-circuits are increased for a particular circuit, how will the fidelity change? So we have taken the 20 qubit circuits for real amplitude and Bernstein-Vazirani for both the measurement mitigation and no mitigation, and we have increased the number of circuits for this 20 qubit circuit, and we can see there is a linear improvement in terms of fidelity. The y-axis is fidelity, x-axis is the number of sub-circuits. So we notice a linear improvement with the increasing number of sub-circuits. But if we increase the number of sub-circuits, there is the classical reconstruction time. So here we can see that this is the post-processing time in y-axis. The number of sub-circuit is same as the previous figure. So there is with an increasing number of sub-circuit, the cut size increases, which leads to an exponential increment in the classical post-processing time for reconstruction of the full probability distribution from the sub-circuit. So this is basically a trade-off. Now what happens if the number of qubits in each sub-circuit, number of qubits are increased? So we are considering bigger and bigger circuit, then how the fidelity changes. So we have taken again the real amplitude circuit, but with different qubits. So a 2 qubit circuit, 3 qubit circuit, and up to 10 qubit circuit for real amplitude and Bernstein-Vazirani. And we have plotted the fidelity, the y-axis. So both the subcircuits are scheduled by our scheduler notads, and fidelity basically decreases with an increasing size of the result. We have done this result after 10 averaging. So this is kind of intuitive. If you increase the size of the circuit, the fidelity will decrease. Now the solution will be to reduce the number of qubits in each sub-circuit, so you have to do the cutting. Now again, if you do the cutting, the fidelity will be better, but you will need more time. So this is a kind of trade-off. Now there is the experimental result on 28 qubit circuit. So previously we have seen the results for 6 qubit and 10 qubit. Now for 28 qubit we don't have any fidelity value for uncut, because we have considered the maximum 27 qubits hardware, so it is too big to be executed on our set of devices. And if we increase beyond 27 qubits, it is also difficult to simulate to get this fidelity value. So here we can see that for real amplitude 28 qubits circuit, if we partition into two sub-circuits, then what is the value for no mitigation and mitigation. So the fidelity is poor without error mitigation, but with mitigation it is 0.7, that is quite good. And it is obvious since the measurement error is the most dominant source of noise in current quantum devices. And one thing to mention is our proposed method is independent of the size of the hardware. The last result here is with what is the change in fidelity with and without scheduling. So what happens if we don't schedule and put them everything in one particular hardware? So here from the heat map, there are the machines, and this is the fidelity value denoted with the color codes. So here we have checked the fidelity of a 16 qubit real amplitude circuit when partitioned into two sub-circuits and executed on all possible hardware pairs. So the maximum fidelity means maximum fidelity is shown when both sub-circuits are run in IBM Hanoi. But if two sub-circuits are executed on IBM Hanoi and IBM Kolkata, so IBM Hanoi and IBM Kolkata, here the fidelity is slightly lower, that is only 1% lower, but the execution time will be reduced to half. And it may be possible that it is not always possible to execute both the circuits on IBM Hanoi, because there are time restrictions in execution time, right? So it is rather more useful to schedule the sub-circuit to two different hardwares using notads than to execute both of them together on similar hardware. So if we can see that, okay, we don't have time to run Hanoi, both the sub-circuits, but we have time to run both of them in Cairo. So both of them Cairo is this block. The fidelity is poor, but if we run one circuit in Kolkata and one circuit in Cairo, this block, this is better in terms of fidelity than this. So this is better. So this holds true even there is some hardware whose maximum execution time can accommodate both the sub-circuits. So notads will find this distributed scheduling and improve the final fidelity of the circuit. Now what we have done using ILP is an NP-hard problem. Hence we have given a graph theoretic approach for the scheduling. Now this graph theoretic approach is applicable only when the number of sub-circuit is at most as the number of hardware, and the maximum execution time, the tau j, is equal to tau min for all the hardwares. Under these two restrictions, our scheduling problem essentially becomes an assignment problem. Therefore, it can be solved polynomially using a graph theoretic approach. So this is our approach. In this figure, we can see a bipartite graph. So in this left side, there are the set of vertices, denotes the hardware, and the right side, there is the sub-circuit. This is two sub-circuit of 6 qubit ripple carry adder. Now each edge of this complete bipartite graph is associated with the mathematical scope we have calculated for the corresponding circuit hardware pair. Now in a bipartite graph, a matching means the collection of edges selected in a manner where none of the chosen edges have a common endpoint. For example, for ripple carry adder, if we chose IBM Q Mumbai, then we cannot use any of these edges from ripple carry adder and any of the edges extended from IBM Q Mumbai. That is matching. Now a maximum matching denotes a matching that has the largest possible size indicating the highest number of edges that can be included. So we want to assign each subcircuit to a hardware such that the mathematics score is minimized. Therefore, finding the optimal noise hour assignment, which is our target, to the subcircuits to the hardware is same as finding the minimum with maximum matching graph. So this becomes a MWMM problem, and this is the matching. So this figure shows the matching. So IBM-Q Mumbai is matched with triple carry adder first subcircuit, and IBM-Q Hanoi is matched with the second subcircuit. It shows the assignment of the two subcircuits as denoted with the red edges. We have verified that the fidelity obtained by the MWMM scheduler is same as the ILP scheduler because they both give the same scheduling in case of this. But if the number of sub-circuits is more than the number of hardwares, then matching is not possible because more than one sub-circuits then have to be scheduled to same hardware. So this is no longer a matching, and hence it cannot be solved using the minimum weight maximum matching method. So to summarize, we have this is basically an optimization approach that combines circuit cutting and mapping to find the least noisy qubits on a hardware for a given circuit without increasing the swap count. It is done using the mathematics and circuit knitting toolbox. Then we have designed a scheduling algorithm to select the best hardware from a list of available options for each of the subcircuits. It requires minimization of noise and minimization of execution time. Both of these don't go hand in hand to hand, so we have to formulate a ILP that aims to achieve the minimum noise and execution time and stick to a fixed allowed execution time. Now this fidelity and execution time obtained by this method on various benchmark circuit, as you have seen, is significantly better than the uncut version when executed on a least noisy device. Now this is an initial step towards noise and time minimized distributed quantum computing, and it can provide promising result for enhancing the performance of current quantum computing systems. So this is the bibliography. Thank you. If there is any question.
Yeah, thanks for the presentation, Debasmita. So if there are like any comments, questions, suggestions.
I have a question, Debasmita. You had a chart where you were showing fidelity of yeah, that one, the next one, across different combinations of machines. Is that 45 page? Good. Can you go to the next page?
Yeah.
Okay. So this one was obtained on a particular circuit, a real amplitude circuit, and it also
Yes.
tried out on all them. Okay. So how do you generalize this idea to any circuit or any combination?
Okay, so this is for a 16 qubit real amplitude circuit, but if we take any circuit, what can happen? So suppose this IBM Q Hanoi, the qubits are better, less noisy, then of course every time this will give you the better fidelity if you run both the subcircuits in IBM Hanoi. Now suppose the qubits of Kairos are not as good as Hanoi, then if you run both of them in Cairo, it will give you a poorer result. Now our target is to not to run both of them in same machine, but to distribute them. So by distributing them, we have stated here that the reduction, there is some reduction of course, but the reduction is not so much bad, but the time will almost be half because we are basically distributing both of the subcircuits. So whatever the subcircuits be, if we distribute it, the time will be lower. And if your question is about fidelity, then it always changes. So if you run in different combinations, so if you run in Mumbai and Cairo,
I think my question is slightly different. I understand what this is trying to tell us. My question is, can you use this as a reference in your allocation or the scheduling one, or when I say generalize, I'm asking if I give you not real amplitude, but some other circuit, can you use your data from real amplitude to make a judgment on some other circuit and then allocate, and you will still have similar fidelity results? Or do you expect any circuit you need to have this plot generated first before you do this allocation?
Okay, so how we have done, if we just go to the mathematic part, because we have started, the first step was mathematics. So in mathematics, what we did is, for a particular circuit hardware pair, we generated the score. Now you are talking, we get for real amplitude, this is the best scheduling. For Bamstein Fajrani also, we use the same scheduling, and what will be the result, right? We have not done this because uh, I think it will differ. The big,
If I can
let's
add a
make
if I
this.
can add a comment here, so Shesha, the heat map generation is not at all necessary. I mean, the heat map generation is just to show that how good the scheduling is, how good the performance of the scheduler is. Once you have the mathematics scores, so that is obviously circuit dependent and hardware dependent. So once you have those scores, you just need to give it to the scheduler. It will not generate the heat map. It will just solve the ILP or the graph theoretic approach, whichever is there, and it will just give you the result. I mean, the heat map generation is done without any scheduling. It is just doing all possible combinations just to check out how
Yes, in the
good
heat
or
map
bad
there
the
is no
performance is.
scheduling.
Okay, I have follow-up questions. I'll circle back. I think there are a couple more people who have questions.
Yeah.
Uh, Hi, Debasmita. This is
Hi.
Chaitanya. Very nice talk. I have three questions. Like, but the major thing is like, what will be this classical computational time in general? Like, how large and how huge this time is? Like, when you are saying like, when you cut the circuits into finer circuits, I think smaller ones, you said that there is an exponential increase in the time. But what is it like roughly? In the sense like, is it like hours, minutes? That way I'm
Yes,
asking.
I have plotted it in second. Okay, so the post processing time here, the y-axis is in seconds, and you can see from here. So if it is a 6 qubit circuit, so if
Six
the
hours,
number of
okay.
sub circuit is 6 for 20 qubit real amplitude, then it is kind of for Bunsen Vazirani is more than 100, and for 100 seconds, and for real amplitude it is about 60 seconds.
Okay. So again, the follow-up question, immediate one is like, what are these circuits depths? What are the sizes of this? I mean, I understand the qubits are like about 20, and then you further reduce them to different size. But what is the circuit size? And my interest in asking this question is like, we deal with chemical systems, and for the chemically inspired answers, generally the circuit depth is very high, even for very small molecules. So yeah.
So yeah, I haven't remember exactly the depth of all the circuits, but here you can see this is the 6 qubit ripple carry adder circuit. So this is the depth for a 6 qubit.
Okay.
Yeah.
Maybe you can talk about the Grover circuit, which had a larger depth.
Uh, yes, for Grover circuit it was larger depth, but we have not included that in our results.
So Chaitanya,
Our
if I again,
Yeah.
if I may just
Sure.
since we were talking about these chemical circuits, so yes, I mean some of the chemical circuits can have really large depth, and so what you need to see is whether that circuit is good for cutting. So what I mean, what Shushmita madam was talking about, that we
thing is,
tried with
yeah,
Grover's algorithm, and Grover's
yes.
algorithm is
So
a very
we
deep
tried to
circuit.
Okay.
Yeah, go on, Debasmita.
yes, so why we have not included the Grover's algorithm circuit in our result, because it is a very deep circuit, and when we cut it, we have seen that it basically increases the number of qubits in the sub-circuits after cutting. So this was not good for this. So I don't think all circuits are good for cutting or this application.
So based on your knowledge, at least like chemically, I mean, for the chemical circuits, do you think that this will be working or it will not be? Debasmita, if you also know, you can tell. Otherwise, whoever is,
No,
just want
I
to
have no
confirm.
idea about those chemical, those
Okay,
circuits. Yeah.
okay, fine, fine, no issues. But it's very nice talk. Thanks. Thank you very much.
Anuj here had a question which is kind of a similar flavor what Chaitanya asked, that does subcircuits introduce any considerable overhead which will increase the number of qubits?
Yes, basically there will be overheads, because that's why the when we increase the number of qubits, so one thing is we increase the number of qubits and we fix the subcircuit into two, then the fidelity will decrease. And one thing we can have do that, we increase the number of qubits, but we increase the number of subcircuits also. And if we increase the number of subcircuit, it will of course come with the overhead because of the classical post-processing time, which is exponential, as you have seen in the graph.
And also adding on to this, what Debasmita said in terms of what Anuj asked is, if I remember well, we did like 4-qubit Grovers or something, and it ended up that you need around 5 cuts or something to just cut a 4-qubit Grover. So
Yes,
what
what
that
I
means,
just said, yeah.
yeah, 5 cuts technically means you now need 5 preparation qubits. So each subcircuit becomes two of the original plus 5, which is 7, which makes no sense. So, I mean, you are then cutting a 4-qubit circuit to make each subcircuit 7 qubits. So you need to like, that is also one reason why not every circuit is amenable to cutting. Apart from the classical post-processing time, you need to also take this into account.
Can you expand on that point? What in the circuit makes it increase the number of qubits? Is there any structure that leads it to
Yes.
have that?
So what you can clearly do, Shesha, you can just if you take each CNOT gate as a vertex, and whenever there are like 2 qubits are connected between CNOT gates, you take that as an edge. So this becomes a graph, and then all you want is to partition that graph, and that means that what is the mean cut at least for that graph. So that mean cut thing can become very high. And if that mean cut is very high, then it is not really a good idea to use that for circuit cutting.
So, as a rule of thumb, you want to look for circuit that have islands of deeply entangled states.
Exactly, exactly.
Okay.
Any more questions or?
Now, that in a way also answers Chaitanya's question from before.
Yes,
In
yes.
quantum chemistry setup, you want to look for your Hamiltonians which have highly coupled locally and not getting into highly entangled global state. And if you have those kind of Hamiltonians, you would want to consider this approach.
True. Thank you. Yeah.
If I may add, what it boils down to is that the way the circuit cutting is working is of course it's trying to get a balanced min cut, and it's cutting the entire circuit over the entire time span. But it may so happen, if it is possible, that you may first, you know, cut it depth-wise, sort of partition it time-wise, and then look at it. And as Sesha is mentioning, the clusters of locally entangled, those are the ones for which you can enhance the execution. And for the others, depending on the availability of hardware size, uh, you may actually go for the uncut version also. So I mean, in the near future, when we get more qubits, better quality qubits, Still, the scheduling problem will be there, but it will have a different flavor, or a sort of a combination of both techniques.
So, a quick question, Debasmita. Given that I know your background, have you considered applying any machine learning instead of solving the ILP?
Yes, yes. Actually, when so ILP is NP hard, so we wanted to give some polynomial time solution or some heuristics. So yes, maybe applying some ML to find the mapping can be good. Yeah.
I'll add to that. ML is good for prediction, classification. As far as optimization problems are, it gets so complicated. The ML models themselves, and things are evolving. Very recently, I think a couple of days ago, Google AI, Quantum AI, has published a paper in terms of quantum error correction, trying to do all kinds of error correction. And just by looking at the model, it's amazing. The number of parameters goes into lakhs. So they have, a recurrent neural network, and within it, they have CNNs, and so itself is a huge thing. And even to execute that, you would need a large supercomputer. So it's kind of a chicken and egg problem.
So instead of where I was going with that idea though, ma'am, is that not to solve the whole optimization problem, but bits and pieces of it through machine learning rather than, for example, assignment of mission, choices of machines to assign. Which combinations do you want to assign to improve the fidelity? Uh, that's a subset of the larger problem that is being looked at. Um, can we learn, given that this characterization data could be available, you could leverage on some existing data, noise characteristics, plus other things that are available readily as data, can some subset of the problem be solved in ML, but the larger optimization could still be an optimization problem to solve in a regular way?
Yeah, it's probably possible, but we'll have to see. Because first of all, even with the earlier machine learning approaches, the size of the data set was in lakhs. Even that was not, it should have been much larger. So getting labeled data of that type itself, or generating that, and if it becomes synthetic, then again we lose the flavor of the challenge. That's what I mean, just off, you know, as an offshoot thinking, as I may say so. But yes, at some point, when things get far more larger, one may try to look at that.
One other follow-up question, Debasmita. So how does this scale as the number of qubits increase? I'm not talking about these. You showed us a plot on the number of sub-circuits increasing. I mean, as the number of sub-circuits increase, this grows exponentially. But in terms of your ILP solution time, you did have a polynomial one. Because we are moving all our fleet to 100 plus qubits as a default now, and we are pushing towards utility scale, which means that your circuits number of qubits is going to be 50 plus, or we'll increase the number of qubits, and the circuits you're going to get is going to get bigger. The optimization problem that you're solving, how does it scale? Is that polynomial thing that you talked about is in the overall end-to-end is still polynomial and the compilation is reasonably quick?
So I think I have to see that, right? Because I have not gone above 28 qubit circuits in this case.
So the CPlex, what it does is basically it uses a LP relaxation. So that's why there is a limitation, as you rightly pointed out, that it does it. But there, I mean, another direction could be going for SAT solvers. But again, as rightly pointed out that if the size of the problem increases, the number of constraints, just as in ILP, the number of constraints and number of variables are going to go. I mean, the blow up is going to be very large, but similarly for SAT solver, we've used it for some other optimization problem, trying to compare both. The quality of the solution is probably the same. I mean, after all, we have very efficient SAT solvers, but the problem is that SAT solvers take much more time than CPLEX. So the question is, this is just for scheduling, not for the actual computation. Uh, and as the quality of the qubits get better, the deeper question is, do we need fast scheduling to get it to execute?
There is one more thing, Shesha, in the spirit of what you asked. Recently, there was a paper by Daniel Egger and Atsushi, if you know him from Tokyo, IBM Tokyo. They have done a paper where they have not done this scheduling, but rather a kind of mapping of particularly QAOA circuits on heavy hex architecture. And they have actually showed that using set solver, most of the time it is extremely fast. It is extremely fast compared even to the transpiler that we have today. But as madam was saying, there are certain scenarios where like the graph size and the circuit size becomes almost comparable. That is when the set solver starts taking extremely high time. And but yeah, it was overall interesting that most of the time you can do better, and maybe we can also think of some other heuristics here instead of ILP. I think Chaitanya had a question.
Yeah, this is probably a general question. So I just wanted to know, like, why we cannot cut this deeper circuits into shallower circuits. Is there a way, like right now you are cutting the circuit by qubit wise, right? Like more qubits to less qubits. But what physically, like, what is stopping us to cut the deeper circuits to shallower circuits in general?
Let me take this. So what is actually stopping you from cutting a deeper circuit? So it is not a problem of deeper circuit. So if you think of a GHZ circuit, right? You can take it to 100 qubits or whatever, 1000 qubits, whatever you want. If you want two subcircuits, all you need to do is to find one point between two CNOT gates, cut it, and you have like two separate circuits. But if you don't have so nice structure, then there it may not be just a single point where you can cut, and the number of points where you need to cut to make to disjoint circuits can start growing. So when that starts growing, the final post-processing time becomes extremely high. One thing. Second thing is that if you are interested mostly in chemistry problems, what we have done here is that we have started to work with fidelity. So that means that we need the final probability distribution. But if you are okay with only expectation value for some observables, this can be faster. So you can, I mean, at some point, we have to stop hoping to cut circuits if we need probability distribution, because the post-processing time is exponential. But if you are okay with only expectation value, circuit knitting toolbox works with that. You can still like, because then the reconstruction is polynomial in the number of cuts, so you can actually go deeper, much deeper than you can expect to go if you want the full distribution. So these are 2 points what you should be thinking of. And the third thing is that what we have done here is something that the circuit knitting toolbox terms as wire cutting, that you, as I said, you cut between two CNOT gates or something like that. But there is also another thing called gate cutting, where you can expect to replace one CNOT gate or any 2 qubit gate using multiple single qubit gates and some physical feed forward, some measurements and things like those. So it's like deciding that how much classical post-processing time you are willing to give. Nothing is stopping you from cutting. You can cut any circuit, theoretically speaking. But practically speaking, you need to decide how much time for post-processing is practical.
So, but when you are cutting this, I mean, when you are considering deeper, you said just now that like we can go to how much ever deep we want. But like based on our normal calculations with the current hardware, we are facing that like whenever the circuit depth is more, the amount of errors that we are getting is like too huge. Like for example, we tried for the H2 molecule with 4 qubits with the CCSD answers, and also the same thing with the different kind of circuit. So when the circuit depth is deeper, we are getting errors in the order of like one hard tree. So that is essentially saying that all our calculations are meaningless. So that's the reason why I asked, like, if we can actually cut down the circuit to shallower ones. We have seen for shallower circuits of the same kind, I mean, different answers. When we used, the errors were pretty low. I mean, in the order of 0.1 had tree versus this is 1 had tree. So in order of magnitude improvement, we have seen for shallower circuits.
I have a question related to this. I did propose that you sort of cluster into, I mean, cut out the deeper circuit, first of all, let's say vertically, and then horizontally, as she showed in terms of the number of qubits. But if you cut it out, into shallower circuits, wouldn't that add to not only, I mean, more ancilla qubits, because after all you would need to measure something and before you feed it to the next stage, so it's sort of, you have a sequence in which you need to execute these shallow circuits depending on the actual deep circuit. So wouldn't that add more or introduce more qubits? I'm just
Yeah,
I mean,
yes, ma'am. Depends on, like, as Debasmita was saying, that for Grovers, if the depth is like so high or it is like so dense that if you want to cut, you end up with like lots of cuts. Each cut introduces one more qubit. So that would also imply that, I mean, a 4 qubit, cutting a 4 qubit in 5 places, and so you have a sub-circuit of 7 qubits. That doesn't make any sense. That will make things worse. So it's like a good thing, maybe, as Madam was saying, to create a graph of that and then try to see at least whether the mean cut may not be good, because the minimum cut may give you like 100 qubit. If you have 100 qubit circuit, the minimum cut may say that you make it 80/20. That is not very useful. So some balanced kind of thing, whether that is even useful, how many cuts you need to make it balanced, that will tell you how many extra qubit goes in each sub-circuit, and also the classical post-processing time. So all of these needs to be taken into consideration. Uh,
I mean, the balanced mean cut or balanced KWA cut itself is NP complete. So you have actually two NP complete problems back to back. Okay.
Thank you. Thanks for that explanation.
okay, if there are no more questions, thank you, Debasmita, for this talk.
Thank you.